So now you know about the Fourier transform, how the Fourier transform works and why it works. And we've discussed how to compute the Fourier transform, how to interpret the results of a Fourier transform. And we also discussed that one of the main limitations of the Fourier transform for EEG data analysis or neural time series analysis is that it's difficult to determine any temporal dynamics in the data. So here we see that there is some component of 25 hertz activity in this signal, but it's really extremely difficult and for all intents and purposes impossible to determine whether this 25 hertz component is constant over time or whether there is a burst of 25 hertz activity here and no 25 hertz activity here and so on. So in other words, the problem is that the Fourier transform tells us about the results over a block of time. But of course, we want to know how the frequency structure in the data changes over time. And as I mentioned before, technically, the temporal dynamics in the signal, all the timing information is inside the Fourier transform, but it's kind of hidden in the phases, and it's not very easy to interpret the results, certainly not from only looking at the power results in a plot like this. The reason why we kind of lose the temporal information, the reason why the temporal information is hidden in the Fourier transform is that each step of the Fourier transform involves computing the dot product between a pure sine wave that is constant amplitude for the entire duration of the signal. So you can think about the weighting function of this step of the Fourier transform with these data. The weighting function would look something like this. So we are equally weighting all of the time points in the signal. And that's why we don't really get good temporal localization with the Fourier transform. So you can imagine if we want to get some temporal localization, we want to understand something about the temporal dynamics. We do not want to use a kernel that kernel that looks something like this. Instead, we might want to use a kernel that looks something like this. So here you can see this looks a bit like a sine wave, only in the middle, and these are zeros here on this side and zeros here on this side. In fact, this kind of signal is called a Morley wavelet. We will be using Morley wavelets a lot in time frequency decomposition. I will speak much more in depth about Morley wavelets in the next lecture. But you can already imagine that computing the dot product between this signal and this dot product, this kernel, is going to produce a weighting function that looks like this. And so this is now going to tell us something about the frequency characteristics in this region of time here, and it's not going to tell us anything about the frequency characteristics here because these are just being multiplied by 0 in the dot product, and it's not going to tell us anything about the frequency characteristics here because this is also being multiplied by zeros. So if all we cared about were this region of time, then the procedure would be fairly straightforward. We would compute the Fourier transform again, but instead of using sine waves, we would use this wavelet. So that would be very simple, very straightforward, except of course that would only give us the temporal localization in here. So what we want is also to be able to understand or extract the temporally localized frequency characteristics at this time point and this time point and this time point and all throughout time. And so you can already imagine that one way of doing this would be to do something like the Fourier transform, but with this kernel instead of with the pure sine wave. But then we want to move this kernel around so that this non-zero part of this kernel or this Morley wavelet is aligned with this part of the data and this part of the data and so on up into this part of the data. This is exactly the idea of time frequency decomposition. We do something like a frequency decomposition, but we get some temporal localization. And so the mechanism by which we do this is through a procedure called convolution. Okay, so now we are going to get into the next section of learning about time frequency analyses, and that is convolution. Convolution can be implemented and it can be conceptualized in two different ways. It can be conceptualized in the time domain, and that's what we are going to focus on in this lecture. And it can be conceptualized or can be implemented in the frequency domain via frequency domain or by multiplication in the frequency domain. It's useful and actually it's important to understand how convolution works both in the time domain and in the frequency domain, because some aspects of convolution make more sense when thinking about how convolution works in the time domain, and other aspects of convolution make more sense when thinking about how convolution can be implemented by multiplication in the frequency domain. But in this lecture, we are only going to discuss time domain convolution. Okay, we are going to be using a kernel, a time series called a Morley wavelet. Morley wavelet is just a sine wave that's tapered by a Gaussian. In the next video, we are going to discuss Morley wavelets in much more depth, how they're created, what they look like, how to make families of them, what they look like in the frequency domain, and so forth. This is just a little bit so you can see where this is going. So here's how convolution in the time domain works. It's like a Fourier transform. You can utilize the knowledge that you have about the Fourier transform to understand how convolution is going to work. It's slightly different than the Fourier transform though. So we start by taking our kernel and our signal. These are the two time series that you need for convolution. The signal throughout convolution, the signal never changes. The signal is always going to stay exactly the same in exactly the same place. And what we are going to do at each step of convolution is move the kernel around in time. Now, each step of the Fourier transform involves computing the dot product between the sine wave and the data. And each step of convolution in the time domain involves computing the dot product between the temporally localized kernel and only part of the data. So here I have the kernel lined up to somewhere towards the beginning of the data, and now we're going to compute the dot product, and of course you know that it's just the element-wise multiplications, and then you sum them together. Now the result of convolution at each step of convolution is plotted at the center of the wavelet. So here we have the wavelet or the kernel aligned with this section of the data, and we do the element-wise multiplication and sum, that's the dot product, and then the dot product is plotted in a location corresponding to the center of the wavelet. So for this reason, it's very useful always to use a convolution kernel, use a wavelet that has an odd number of data points. If it has an odd number of data points, then of course there is an exact center with the same number of points behind it and in front of it. In fact, when you're making Morley wavelets, this is very easy to accomplish simply by defining the wavelets using a time vector from negative something to positive something. So for example, if we create this wavelet to go from -2 seconds to +2 seconds, then we'll have 2 seconds on this side, 2 seconds on this side, and we have 0 in the middle. So that's going to guarantee that we will have an odd length for the kernel, so that's very useful. Okay, so this is one step of convolution. The next step of convolution is to keep the data exactly the same, and we take the kernel and we just slide it over by one time step. Now here, of course, I moved it over quite a bit, but that's just for illustration purposes. In practice, you move the convolution kernel over by the smallest time step that you have, so just by one time unit. And then you repeat the whole procedure again. You compute the dot product, you plot the dot product in a location corresponding to the center of the wavelet with respect to how it is aligned with the data. So, and then you keep doing this procedure over and over and over and over and over again until the wavelet gets to somewhere at the end of the data, and then you have this time series of dot products, and this is the result of convolution. Okay, so now we can look at this again in a simpler version. Here is our signal, here's the kernel, and the result of convolution is going to be the dot product plotted at a location corresponding to the center of the kernel as it's moving across time. Here you see the result of convolution, and it looks a bit like the kernel is being smeared across the signal. So imagine taking this kernel and kind of smearing it across this signal over time, and you would get something that looks like this. So it's something that looks a little bit like the signal, it looks a little bit like the kernel, and it's kind of like if you would merge them together, then you would get something like this. When we talk about doing convolution via frequency domain manipulations, this will make even more sense how the result of convolution is a result of both the signal or the result of characteristics of the signal and characteristics of the kernel. Okay, what I would like you to think about now is what is the relationship between the result of convolution and or the length of the result of convolution and the length of the original signal. What you might notice is that the result of convolution is a little bit shorter than the original signal. So it starts a little bit after and it ends a little bit before. That makes sense when you see how we implemented this mechanistically, because we aligned the kernel with the signal in order to perform the dot product, because of course you can only perform a dot product between two vectors that have the same length. And that means that and because the result of the convolution is plotted at a location corresponding to the center of the kernel, we're actually losing a few points here in the beginning, and same story for here at the end. Now, maybe you look at this example and you say, well, it doesn't really matter. It's only a couple points in the beginning and at the end, and there's zeros anyway. There's nothing interesting happening in the signal here. That's true. In this particular example, we don't really lose any information, but keep in mind that the length of the kernel is arbitrary. The kernel can be as long as we want it to be. Imagine what would happen if the kernel were as long as the data. Then all of convolution would just give us one single data point here at the center. This would be just one dot product, and this is not very useful. This provides no temporal information about the characteristics of the signal. So, in practice, the way that convolution really works is that convolution starts such that the rightmost point of the kernel is aligned with the leftmost point of the signal. And that means there's only one point of overlap. So in some sense, the dot product is not defined. And so what we need to do to be able to compute a dot product is zero pad the signal. So we add to the beginning of the signal however many zeros we need in order to define a valid dot product between the convolution kernel and the data when the convolution kernel is, when the rightmost point of the convolution kernel is aligned with the leftmost point of the data. Sometimes this is easier just to see how it works than it is to explain it verbally. Of course, because the result of convolution is plotted at a location corresponding to the center of the kernel, you can see now this means that the result of convolution is actually going to start even before the signal starts, right? And now we move convolution along, and then convolution ends when the leftmost point of the convolution kernel is aligned with the rightmost point of the signal. And here we run into the same problem. The dot product is not defined here, so we need to zero pad the signals. And of course this doesn't really matter because we're just adding zeros. So 0 times whatever's in the kernel is just going to give us 0. So these zero padded points don't really contribute to the result of dot product, but they do make the result of the dot product a bit longer, like this. Okay, so let's see this example again with EEG data. So here we have our snippet of EEG data. And we're going to start convolution. So here's our convolution kernel. It's a wavelet. And we start convolution such that the rightmost point of the wavelet is aligned with the leftmost point of the data. And again, we have to zero pad all the way out here so we can define a dot product. Here I've drawn this vertical line here to remind you that the result of convolution between this wavelet and this data is going to start here. So the first point of convolution, the first point in the result of convolution is going to be in the center of the wavelet, which is all the way out here, well before the EEG data actually start. Okay, and as we run convolution along, you can see that the wavelet slides along the data, and convolution ends when the leftmost point of the data is aligned with the rightmost point of the data, and of course we have to zero pad out here. And convolution, or the last point in the result of convolution, is going to be here, corresponding to the center of the wavelet. So here's what the result of convolution will look like in this case. So you can see that the result of convolution is actually longer than the original signal. How much longer? Well, you can see it's because the result of convolution at each step always corresponds to the center of the wavelet. The result of convolution is 1/2 of the length of the wavelet too long at the end, and is 1/2 of the length of the wavelet too long at the beginning. And so the length of the result of convolution is the length of the wavelet plus the length of the data, and we have this -1 here. So this always trips up people. Why is it -1? Where does this -1 come from, and how do we understand that? I think it's easier to understand this by seeing a simple example than by trying to work out exactly why there's the -1. It's basically because they overlap at one point here. But here we have a toy illustration to depict this. So here we have our data, which is length 4. We have the kernel, which is length 3. And what we are going to do is perform time domain convolution between the data and the kernel, and the result is going to be plotted here. So convolution begins with the rightmost point of the kernel being aligned with the leftmost point of the data. And of course, we have to zero pad here in order to compute a valid dot product. And the result of convolution gets plotted here at this location corresponding to the center of the kernel. So here is the result of the first step of convolution. And now what we are going to do in convolution is move the kernel one time step over so the data stay the same. The kernel gets slid over by one time step. And now we compute convolution, we compute the dot product again, and the result of convolution is going to go here. And now we continue along all these steps of convolution. Here is the final step of convolution. You can see the leftmost point of the kernel is aligned with the leftmost point, the rightmost point of the signal, and of course we zero pad here. And now look what's happened. The data are length 4, the kernel is length 3, and the result of convolution is length 1, 2, 3, 4, 5, 6, which happens to be the length of the data plus the length of the kernel -1. So I hope this is clear why the length of the result of convolution ends up being n plus m, that's how we typically say n plus m -1. This is a really important feature of convolution to remember, and you really have to memorize that convolution, the result of convolution, is always length m plus n -1. This, when you do convolution in the time domain, it kind of falls out of the process naturally. You don't really have to plan for it or think about it. But when we do fast convolution via frequency domain multiplication, this becomes incredibly important because you will have to remember to implement the Fourier transforms using the valid length of the result of convolution. I'm stressing this because it's possible, and it's unfortunately very easy to get convolution wrong by not remembering this result. And in this case, this is a situation where you can get it wrong and MATLAB will not produce an error. So your MATLAB code will run without producing an error, but the result that you will get is not a valid convolution. Okay, we will discuss that in gory details in the future when we talk more about convolution via frequency domain. Okay, So now you see the result of convolution is a bit longer than the data. And so you can stop right here. This is technically the end of convolution. We have finished convolution. But in practice, it is very common to cut off the beginning of convolution and the end of convolution such that the result, the final result of convolution is the same length as the length of the original data. Yeah, this is convention. This makes things much easier. It's not technically necessary, but it's something that you should do. Okay, so let's see how some of this stuff looks in MATLAB. So here in this first cell, I'm defining a signal, and in fact we are just going to recreate one of these slides I had in the PowerPoint. Here we are going to use MATLAB's function conv to compute convolution between the signal and the kernel. This last third input into the function conv is same, and that just asks MATLAB to return the result of convolution that is the same length as the signal. And so that means that MATLAB is going to be cutting off the beginning and the end for us, so we don't need to do that ourselves. Okay, so here plotting the signal, plotting the kernel, and plotting the result of convolution using the MATLAB function conv. This is just the same thing that I showed in the PowerPoint slide. Now here in the second cell, this is where we are going to compute convolution in the time domain manually. Here you can see I'm zero padding the signal. So we have the signal in the middle, and I'm putting zeros on either side. How many zeros do we need on either side? Half the length of the kernel. So that's what I define here, half the length of the kernel. Here we are initializing the output of convolution, or the result of convolution, and you can see how long is convolution going to be. Length n plus length m minus 1. And here's where we actually run the convolution. So we are looping over time points, and at each time point we are computing the dot product between the kernel and the data. And now, so I didn't discuss this in the lecture slides, but when you implement convolution in the time domain, then the kernel gets flipped around backwards for technical reasons that are not really important to discuss. So the kernel gets flipped around backwards. You don't have to do this when you implement convolution as frequency domain multiplication. So you don't have to worry about this too much. The important thing to see here is that at each time step, we are computing the dot product, so it's the element-wise multiplication then sum between one part of the data and the kernel. Okay, and here at the end, we are going to cut off the first half of the length of the convolution and the last half, the length of the kernel, and we're going to cut off half the length of the kernel from the end. And now we can make a plot. And this just shows that the result of our time domain convolution closely or perfectly matches the result of the MATLAB conv function. So the most important thing to remember from this video is that the length of the result of convolution is m plus n minus 1. That's very important. So now in the next video, or in the near future, we are going to discuss how convolution works through the frequency domain, and I hope you found this video interesting and informative.